This is lecture 23. So we were discussing in the previous lecture the effects of Y22 or GDS uh, uh, to our common source amplifier, and we saw that if we incorporate the effect of non-infinite output impedance or non-zero output conductance, right? So if this is GDS grounded in our common source amplifier, this was the this becomes the model. And if I have an output load marked as GL and we are taking the output across the output load, what do we observe? We observe that V0 over Vi became minus Gm over GDS plus GL, and naturally this is a lower value of gain than that we have gotten in the absence of GDS. So what was the solution? The solution that we came up with was use a current buffer, right? So what is a current buffer? Again, a current buffer is a contraption that helps in pushing the current from a non-ideal current source to a load without the effect of loading, right? So in our case, our so this our non-ideal current source was this section of GMVI and GDS, right? This was a non-ideal current source. We have a load RL or GL. Let me call this as RDS, RDS1, and let me call this GM1, just to ensure that we are using the right consistent notations from previous lecture, right? So what do we need to do? We needed to put a current buffer in between. So we needed to put a current buffer in between, so that once we connect these, the amount of current that flows in, so this is Gm times Vi, or in this case the amount of current that flows in should be minus Gm times Vi, right? So it's approximately minus Gm times Vi, and that was possible only if the looking in impedance, right? So Rn would have been approximately 0, or in other words, Rn is much less than Rds, right? So this was the one of the bare minimum requirements of a current buffer. What was the other requirement? The other requirement for a current buffer obviously is the fact that the output impedance R out, right, has to be much greater than RL, because a current buffer is nothing but a current controlled current source. Okay, so and how did we do this? We had already seen that what is a current buffer? A common gate amplifier can act like a current buffer, and then we said that so now what we need to do is to replace this block, right? Replace this block with a common gate, correct? So again, what is the incremental model of our common gate amplifier? So now what we can do, we can put, so this becomes GM1 VI. This is GD, let me call this RDS1. RDS1, we have the load RL, and we had to put a common gate amplifier, and we had used a common gate amplifier before, and what is it? It is nothing but a contraption whose using a MOSFET whose incremental gate is grounded, right? Whose gate is incrementally grounded, and if we call this node as Vs, this current becomes Gm times minus Vs because gate is grounded. And just like any MOSFET, we cannot neglect the output resistance, right, anymore, because we now know that the output resistance is a reality, right? And we connect this here, and this becomes our V naught. Okay. Well, and then we further saw that, then what did we further see? We further saw that the short circuit current, the equivalent Norton equivalent model for this, so if this is RL, and we call this ISC, and this are out. So Norton equivalent model for this was ISC was almost equal to GM1 times VI under the condition that, what was the condition? If the looking in impedance, right, looking up impedance into the source of the common gate amplifier would have been much lesser than RDS1, right? So if whatever this Rin was, if Rin is much less than RDS1, so in other words, this translates to, i.e., if GM1, i.e., what was the looking in impedance? Looking in impedance was 1 over GM1 plus GM2 plus GDS2. This is the looking in impedance when the output was short circuited, right? So because we are trying to figure out what ISC was, so that is an important thing that you should keep in mind. So when this looking up impedance, this is Rin, was much lesser than RDS1, right? So this was the requirement, right? So this is Rin when V naught is 0. So that is an important consideration, because otherwise the Rin will be different. Okay. Okay, and what was R out? And we also saw that R out was the summation of these two resistances, summation of RDS1 and RDS2, which naturally should appear, but we had one additional term, and the additional term was GM2 times RDS2 times RDS1. Correct? And then we further argued that it is expected that in saturation this term will be much greater than 1, GM2 times RDS2, because ultimately in saturation we want an amplifier to be to behave like a transistor, to behave like almost like a current controlled, voltage controlled current source, which means its output impedance should be closer to infinity. Infinity is not possible, but which means the output impedance should be very high, and also we are expecting GM to be very high, so we are expecting GM times R to be very high. So it is expected that GM times R should be much greater than 1. If that is the case, in saturation, your R out almost becomes equal to GM2 RDS2 times RDS, right? Right? Okay, so this is assuming GM2 RDS2 is much greater than 1. Okay, so now couple of jargons. So in a common source, in an amplifier, right? In an amplifier, if I go back to this, uh, to the common source amplifier model, right? So in the absence of, right? So when GL is equal to 0, right? When GL is equal to 0, i.e. RL is equal to infinity, what is V naught over Vi? V naught over Vi will be minus GM1 times minus GM1 by GDS1. Correct? Right? So what does this mean? It essentially means that even if your load is infinite, you are not getting infinite gain. Right? In an ideal common source amplifier, if it were an ideal voltage controlled current source, then if we had an infinite load, if RL would have been infinity, then the voltage across that infinite load should also have been infinity. But in this case, clearly that is not possible because the transistor doesn't have an infinite output impedance, right? So even in the absence of RL, you are going to get a finite gain, and this gain, which is limited by the characteristics of the transistor itself, is an intrinsic property of the transistor, and we call this the intrinsic gain, right? So essentially we call GM1 over GDS1 to be intrinsic gain of a transistor. Okay, so what is the intrinsic gain of this guy? What is the intrinsic gain of this guy? The intrinsic gain of that guy is basically the GM associated with that block times the impedance associated or the resistance associated with that block, right? So what is that intrinsic gain? So this essentially becomes intrinsic gain of the block GM2. So essentially this becomes the intrinsic gain of this contraption. So why am I saying all these things? I am saying all these things because it seems like the output impedance, right? Output impedance of this contraption. So this output impedance, or in other words, the output impedance looking here, right? In the absence of the current buffer would have been RDS1. In the presence of current buffer, so in the absence of current buffer, the output impedance would only have been RDS1. In the presence of current buffer, it seems like the output impedance has gotten amplified by the intrinsic gain of the current buffer, right? So this is the intrinsic gain of, this is the intrinsic gain of the current buffer or the common gate stage. Correct? Okay, so this is a very important property. This is a very important property of it that you will often see in many places, that in order to increase the output impedance of an amplifier, often we pass the current that is coming out of a common source stage through a common gate stage, right? Uh, so that the output impedance increases, and this contraption is also called a cascode block, right? So this is also called, let me use a different page to talk about this. So this, the current buffer, the combination of a common source and a common gate stage to increase the output impedance is also called a cascode configuration. Cascode. Please note the spelling is CASCODE, not cascade, the cascode configuration. Okay, so many times you will hear people saying, why don't you use cascode? Moment you say that you have a low output impedance, you might hear people say, why don't you use cascode? So cascode, by that essentially what one means is, why don't you pass the current from the common source stage through a common gate stage, right? Okay, so now that we know what this is, at least what the incremental circuit looks like, we need to then take the next step and see what will be the what will the circuit look like when we replace the incremental equivalence with the MOSFET, right? Ultimately, we have to put the circuit together with the MOSFET. So let's do that, right? So let me quickly sketch the incremental equivalent once again. So this is Vi, right? So this is the gate of the first MOSFET. So this is GM1 times Vi, and you have this output impedance GDS1. Then the gate of the second MOSFET is grounded, right? So this is VG2, this is grounded. So this is GM2, VG2 minus Vs, and we have VDS2, and this output is obviously connected to a RL. Okay, so now let's replace this stuff with a, so let me put the RL on top so that I can save some space here, right? So let me put the RL here. Okay, so now what is the basic thing we need to do? So basically wherever you see this contraption, you replace that with a MOSFET. So here comes one MOSFET, right? So let's call this M1. Again, what do you have on top of this M1? You have another MOSFET. Let's call this M2, correct? And on top of that, what do you have? You have a resistance RL, right? And now we need to bias, right? So how do you bias? M1 is a common source stage. So how do you bias a common source stage? We know it by now, we have done it multiple times. So this becomes the common source bias, right? So we call this VGQ1. Okay, how would you bias the transistor M2? So clearly you cannot leave it floating. Can you keep it grounded? I cannot keep it grounded because of what? Because ultimately I need I need to bias the transistor in such a way that some current flows, right? We need some current, let's say some current I naught to flow in this stack, right? Okay. So by the way, before we proceed, can you tell me who is setting uh, the current in this stack? Clearly, the current in this stack will be set by M1. So what do I mean when I say who is setting the current in this stack? What I am essentially saying is which one is uh, on what factors does I not depend on? What are the primary factors on which I not depend on? So what does I not depend on in a transistor? It depends on, primarily it depends on the VGS, provided the transistor is in saturation. Now as a designer, we have to ensure that the transistor actually remains in saturation, right? So we can work backwards and we can assume to start off that the transistor is in saturation, and since I naught depends on VGS, so we can identify which is the transistor that is setting the VGS, right? So in this case, M1, the gate of M1 is VGQ. What is the source of M1? The source of M1 is grounded. So the VGS of M1 is VGQ, which we are setting separately, right? So since we are setting separately the VGS of M1, the current I naught will be determined by the VGS of M1. Now one might argue that what about the VGS of M2, right? What about the VGS of M2? Is M2 VGS setting the current? I would argue no, because, so let me take you back a couple of lectures where we were discussing this. Let's assume that we need to bias this transistor M2 with a constant current source of value I naught. How do you go about biasing this? How do you go about biasing this? Clearly, this will auto bias as long as we ensure that the gate of M2 is of certain value, correct? So we need to ensure that gate of M2 is of some VGQ2, some value VGQ2, right? And what will that value be? So for this, we need to ensure that there is at least some voltage across I naught, right? There should be some voltage across this current source I naught, otherwise the I naught might shut off, and whatever that some voltage might be is a specification for the I naught, and let's assume that specification is V I naught min, right? If this is V I naught min, what will be the voltage? What will be the voltage required at VGQ2? So clearly your VGQ2 minus V I naught min will be what? Will be the threshold voltage for M2 plus the overdrive for M2, which means VGQ2 has to be what? It has to be at least V threshold voltage 2 plus V overdrive 2 plus V I naught min, correct? Okay, so this we already had decided. And what did we decide on how to bias RL? I mean, this is the simpler part. We can simply say that this is connected to VDD, and as long as VDD is high enough, we need to ensure that we can ensure that M2 remains in saturation, right? So that is the easier part, because here the voltage is I naught times VDD minus I naught times RL. Okay, as long as we ensure that VDD minus I naught times RL is greater than VGQ2 minus 1 threshold voltage, we are good, right? So fine. So now why did I come back to this? This we had already discussed. The reason I came back to this is what is our cascode stage now? What is this I naught now? This I naught is now, instead of I naught, we have a transistor. And what is that transistor? We have the transistor M1, right? So uh, let me draw that. So instead of I naught, we have the transistor M1, which is probably biased with some voltage VGQ1. If this transistor is in saturation, what will be this current? This current will be some I naught or some IDS Q, right, corresponding to I naught, corresponding to M1, right? Okay, so then, so now, can you tell me what is the minimum voltage that is required to keep M1 in saturation at this node? What is the minimum voltage? So this node, let me call it Vs, right, or let me call this Vs2, right, because it's the source of M2. So let me call this Vs2. What is Vs2 min? Vs2 min will be VGQ minus threshold voltage of the first transistor, right? This has to be VGQ minus threshold voltage of the first transistor. Anything above this is fine, but you cannot go below this, right? Fine. So if this is the requirement, of VS2, what has to be the requirement of this guy? What has to be the requirement of VG2? VG2 has to be 1 VGS above VS2, right? So this, note that this voltage drop is VGS2. So this voltage VG2 has to be VS2 plus VGS2. What is VGS2? What is VGS2? VGS2 has to be equal to, this is, we saw it here, right? Right? So VGS2 has to be equal to V threshold voltage of the second transistor plus V overdrive of the second transistor. So what does VG2 need to be? Therefore, VG2 needs to be VS2 plus this, right? So what is VG2? VG2, let me write it in a different line so that it makes sense. So your VG2 has to be, since VG2 is VS2 plus VGS2, this has to be VS2 min is VG. So this is, so VG2 has to be this, which in other words, VG2 has to be at least greater than, VG2 has to be greater than equal to VS2 min plus VGS2 for a current of IDSQ, right? For a current of IDSQ, right? So this is equal to I just plug in the values, so this becomes VGQ1, this is VGQ1 minus V threshold voltage 1 plus VGS2, which is V threshold voltage 2 plus V overdrive, correct? So in other words, this is equal to what? V overdrive of the first transistor of M1, right? So V overdrive of the first transistor plus V overdrive of the second transistor M2 plus the threshold voltage of the second transistor, right? So means that VG2 has to be greater than equal to, so as long as we can ensure that VG2 is greater than equal to this under quiescent state, at least, we can ensure that the transistor M1 is in saturation. Why do I say M1? The reason I say M1 is, let's assume that VG2 is lower than this value. Okay, so let's assume VG2 is lower, right? So let's assume after doing all the maths, we found out that, let's assume we found that assume threshold voltage of 1 and threshold voltage of the second transistor are 1 volt. Let's assume the overdrive voltage is also 1 volt, for both the transistors. Need not be the case, because note that overdrive is a function of the size of the transistor. But to make our life simple, let's assume that uh, the overdrive of both the transistors are also equal to 1 volt, right? So if that is the case, what do you need to ensure Vg2 to be? So Vg2 should be at least greater than VOV1 1 volt, VOV2 2 volt, and VTH2 is 2 volt, 1 volt, which means this should be at least greater than 3 volt. Correct? So what happens if, let's say, this is not 3 volt? So let me put the values together once more. So let's assume that what did we assume? Let's say this is equal to 3 volt. So this is 3 volt. I should use a different color maybe. Okay. If this is 3 volt, what is VGS2? VGS2 is 1 overdrive. VGS2 is threshold voltage of 2 plus overdrive voltage of 2, which is 2 volt. If the gate is of 3 volt, threshold volt VGS2 is 2 volt. What is the source of M2? This is 1 volt. So in order to keep, let's say, M1 in saturation, right? In order to keep M1 in saturation, what we need? This is something that we have discussed earlier, but not in this context. So what we need? VGQ1 to be. So VGQ1 has to be less than VS2 plus 1 threshold voltage. Correct? So which means this has to be, implies VGQ1 has to be less than 2 volt, right? So let's assume, let's pick a number. Let's put it at 2 volt. Why pick a number? Let's put it at 2 volt. So let's say this is 2 volt. Okay. So let's remove this. Okay. So now tell me, okay, tell me one more thing before we proceed. What do you think has to be the value at the drain of M2? At least it has to be greater than the gate voltage of M2 minus 1 threshold voltage of M2, right? So which means that this has to be at least 2 volt or higher. Let's pick a different number. Let's not keep it right at the edge. Let's say this is 2.5 volt, or let's say this is 3 volt. Okay. What is the drop across RL? The drop across RL is IDSQ times RL, right? So that might be some value, and let's assume that we have chosen VDD to of an appropriate value to keep M2 in saturation. Okay. So now let me tell me what's going to happen if I reduce the voltage gate voltage of M2 from 3 volt to, let's say, 2.5 volt. Okay, even before that, tell me what's going to happen if I increase the gate voltage of M2 by, let's say, plus 100 millivolt, 0.1 volt. What's going to happen to the what's going to happen to the circuit? Will the current in the network change? To the first order, will the current in the network change? So herein you have to understand who is setting the current in the network. So if both the transistors M1 and M2 are in saturation, right? If both the transistors are in saturation, is IDSQ likely to change? Clearly not. I mean, you can neglect the effect of channel length modulation for the purpose of this analysis, right? So if we neglect the channel length modulation, and if M1 and M2 are in saturation, right? So IDSQ will depend solely on VGS1, correct? So if we neglect channel length modulation, if CLM is neglected, right? So the current IDSQ solely depends on the VGS of M1. Why? Because the source of M1 is grounded, you cannot change the source voltage, but the gate of the M1 is dependent on you. You are driving the gate, right? So essentially IDSQ is only dependent on the VGS of M1, which means for M2, M1 behaves like an ideal current source. So if M1 acts like an ideal current source for M2, changing the gate voltage of M2 should not change the current in that stack, correct? If changing gate voltage of M2 does not change the current, what is the only likely scenario? The only likely scenario is the VGS of M2 will not change, right? So essentially what I am trying to say is, if M1 and M2 are in saturation, IDSQ depends only on M1 and not on M2, right? Since it only depends on M1 and not on M2, what is the implication? The implication is, this implies VGS of M2, that is VGS2, is constant. VGS2 does not change even if you change the gate voltage of M2, right? So if VGS2 does not change, what does that mean? It means essentially that if VG2 is increased, then VGS2 will also increase. By how much? By exactly the same amount. Because if it doesn't increase by the same amount, right, what's going to happen? You will not have VGS2 to be constant, right? So this, since VGS2 has to be constant due to constant current bias for M2, right? So what's going to happen here? So now coming back to the point, if the gate of M2 goes up by 100 millivolt, the source of M2 also has to go up by 100 millivolt. So this will also go up by 100 millivolt. If this goes up by 100 millivolt, will the current through M1 change? Neglecting channel length modulation. If you neglect channel length modulation, if you increase the drain, if you change the drain to source voltage of a transistor, should the current change? No. Now again, one might argue that it should change now because we have been including channel length, we have been including GDS. But again, you should understand that when to neglect something and when not to. In this case, there will be some change, but that change will be minuscule with respect to the quiescent. Since the change will be minuscule with respect to quiescent, we can neglect the minuscule change. But when you are doing incremental, you cannot neglect GDS because you cannot neglect anything with respect to 0, right? So again, coming back to the same point, if I circle back to wherever we started, who is setting that source voltage of M2? Clearly the gate voltage of M2 is setting the source voltage of M2. The source voltage of M2 is not constant. If I increase gate voltage of M2, the source voltage of M2 will also increase. Okay, great. So this is all good. But what happens if I reduce the source voltage? If I go by minus 0.1 volt, by the same logic, what will happen? What will happen to the source of M2? This will go by, this will also reduce by minus 1.1 volt in order to keep the VGS to same. But now let's turn our attention to M1. What do you think is the biasing condition of what do you think is the operating condition of M1 now when the source or the drain of M1 or the source of M2 has reduced by 100 millivolt? Clearly M1 is not in saturation anymore, right? Because now the saturation condition of M1 is getting violated. Okay, right? So what was the saturation condition of M1? We had to ensure this condition, and this condition is no longer valid if the source voltage falls from 1 volt to 0.9 volt. So what is the solution? You cannot really, I mean, what is the reason? What is the reason of this problem? That this problem arose because we were biasing the transistors right at the edge. We are biasing the transistors right at the edge of saturation. For which transistor? For right at the edge for M1, not for M2, right? Because the way we took the values, note that the gate drain of M2 is 3 volt. For M2 to go out of saturation, we had to increase the gate voltage of M2 to beyond 4 volts. Then only M2 would have gone out of saturation. But in this case, if we bias that gate of M2 to a lower voltage than 3 volt, it seems like M1 will go out of saturation, right? So since this is not a viable condition, so what we need to do, we need to ensure that we don't bias it right at the edge. We have to ensure that for a proper health of the transistor M1, we have to ensure that the gate voltage of M2 should be higher than 3 volts. So this is 2 volt, right? So this has to be then greater than 3 volt. Let's pick another value. Let's pick like 3.5 volt, because and this was supposed to be 3 volt, right? So this was 3 volt. By the way, who is setting the 3 volt? This 3 volt is set by, because we expect a current of IDSQ. This is VDD, right? So this voltage is VDD minus RL times IDSQ, and let's assume that we have chosen VDD and IDSQ in such a way that this is 3 volt. If this is 3 volt, I need to ensure that the gate of M2 is not above 4 volt. So we chose this to be about 3.5 volt, right? If this is 3.5 volt and under the conditions of P overdrive, whatever we chose, what will be this voltage? This will be approximately 1.5 volt. If this is 1.5 volt, what do you think is the health of M1? Even if this guy drops by, for some reason, if the voltage at M2 drops by 100 millivolt, this will drop by 100 millivolt, and still we are good, right? Now the reason why it should drop is, we'll see later, right? You can have different temperature variations, you can have non-robust biasing, all those conditions, because of which the voltage at the gate of, voltages at various nodes can change. But we should always keep in mind that during design, we should not make a design which is just at the edge of working, right? We need to have some margin. We need to ensure that the transistors are not biased just at the edge of cutoff or just at the edge of saturation, and hence we decided to, in this case, we decided to increase that voltage, bias the voltage of M2 in such a way that both M2 and M1 are comfortably in saturation, even if things change slightly. Okay.